Hi everybody! Today I'll be talking about autonomous AI agents for cloud cost analysis. Specifically, how we can build intelligent systems that help organizations understand and optimize their cloud spending. We'll look at both the planning and execution aspects of these systems, and I'll share some practical insights from real-world implementations. Before diving in, let me introduce myself. I'm Ilya, currently working with cloud infrastructure and developer tooling at Spotify. I've been fighting LLMs last 2 years with a specific focus on rack system and production AI agents. Now let's talk about why cloud cost management is so challenging. The rising complexity of multi-cloud environments with their intricate pricing models make it difficult to maintain a comprehensive view of cost. Access to cost data is often limited to specialists and experts, creating bottlenecks in organizations. Knowledge about cost optimization tends to be siloed within teams rather than being broadly accessible. And finally, most organizations find themselves in reactive approach to management, responding to high bills after they arrive, rather than proactively optimizing beforehand. These challenges create a perfect opportunity for AI assistance. Traditionally, cost analysis has been a very manual process with several challenges. First of all, there is a significant technical expertise gap. You need SQL proficiency and deep knowledge of cloud billing data models. This process is resource intensive and diverts valuable engineering time away from core product development. And there is inefficiencies of repetitive queries and error-prone manual analysis. And on the right side, you can see that even ChatGPT thinks that you need a safety helmet when working with SQL. Our first attempt at solving these challenges was the workflow agent. We used a single agent approach where one LLM was handling all questions without specialization. As you can see on the graph, first we would process user question and detect its type. Then we would route this to either use Spotify internal knowledge base, or using rates, or generate SQL to ask billing dataset. And then based on these answers, we would just forward them to the user. Now, this approach worked relatively well, but there were a few issues with it. The first one is SQL reliability. We were generating SQL directly without validation or repair mechanisms. And also system struggled with complex multi-part questions that require different types of expertise. To solve these and other challenges, we decided to work on the next iteration of the agent. One of the key challenges we identified is that LLMs often struggle with precise math calculations, which are essential for financial analysis. Even advanced models can make small but significant errors in calculations that compound over time. Our solution to that was to implement a React agent that generated Python and executed it in Sandbox. This approach allowed us to delegate precise calculations to Python to ensure greater reliability. And you can see the example of the code that the agent generated to compare cost difference. To address SQL reliability issues, we developed specialized SQL expert agent with self-healing capabilities. This agent generates contextually aware SQL specifically optimized for BigQuery, where we can keep most of our data. The key change here is the self-healing mechanism that automatically detects failed queries and repairs them. It can make up to 3 attempts to fix a query before failing back to alternative approaches. The agent also handles result formatting, returning clean data back to the main agent. On the diagram, you can see that we have main query generation node that sends query to the execution node. If we encounter any errors, we'll send that information back to the query generation node and try to repair it. Once we have final working solution, we'll format the results and send it back to the user. For questions that require external knowledge, we implemented web search capabilities using React pattern, which combines reasoning and action for dynamic search. The system can perform iterative refinement, improving search queries based on the initial results. We leverage Google Search API with Gemini models for grounding to ensure that the system has access to up-to-date information. On the search flow diagram, you can see that React agent would first think if it needs to search for information, and then sends it for retrieval. If that's not enough, it will do more searches as much as needed. And then when it thinks that it's enough, it will return information back to users. For complex questions, we needed a more sophisticated planning approach. Our task planning architecture has three key capabilities. The first, task decomposition breaks complex questions into manageable subtasks. Then, workflow orchestration determines execution sequence with dependencies, so we can optimally launch them in sequence and in parallel. Finally, agent delegation maps tasks to specialized agent capabilities. On the right, you can see the example of the simple task plan in JSON format. So first, system decided to call SQL expert to retrieve last month's cost by project. This data then getting into Python expert that analyzes cost trends over time, which then calls cost engineer agent to identify anomalies and root causes. A critical aspect of our architecture is verification and replanning. We use LLM as a judge approach to verify answer quality and completeness. When information is incomplete, the system generates new tasks to fill the gaps. It can also identify inconsistencies and provide fixes through error correction tasks. The verification flow diagram that we have shows that after all the tasks are executed, task results are being sent to replanner node that analyzes if this answers original user questions. If it's not, then it'll generate new tasks to send to execute node, or if it's incorrect, it will also issue new correction tasks. After those new tasks are executed, replanner node will assess again if that answers user questions. If it's yes, then it'll try to format the final answer to exclude all the thinking process and present nicely formatted answer to the user. So putting it all together, here's our complete multi-agent architecture. The user query first processed by planner node, which generates a list of tasks. These tasks then executed by specialized expert agents, including Python, internal knowledge, rates data, SQL queries, or Google search. After execution, replanner node evaluates the results and either delivers final answer or creates a new plan for additional execution. This modular approach allows us to continuously improve individual components and expand capabilities over time. So let's look at the concrete example of how system reasons. This example shows the system searching over Google Docs to find relevant information about cost analysis question. We also have reasoning trace that shows how agent breaks down the problem, searches for information, and combines finding to generate comprehensive response. Here's another example showing Python agent performing math calculations. The trace shows that we first go to rate expert to get up-to-date rates information on standard storage. Then this information is being used by Python expert that writes Python code and executes it in the sandbox. This produces very reliable responses every time and reduces hallucinations by a lot. To measure effectiveness, we build a comprehensive evaluation infrastructure. We use OpenEvals framework, which implements LLM as a judge evaluation with detailed reasoning. We focus on binary correctness assessment with detailed reasoning capture to understand why a response is correct or incorrect. Our data pipeline flow consists of three main steps. First, we extracted real user questions from Slack channels. Then we use thread summarization to generate question-answer pairs. And finally, we integrated all of that data with Google Sheets for easy access and analysis, because we want to make it accessible for non-technical users as well. Our initial evaluation results show significant improvements. The multi-agent approach achieved 58% accuracy compared to just 22% for workflow baseline approach. It's over 150% improvement. These evaluations based on real user questions from Slack covering diverse question types and were compared against expert reference answers. The key improvements came from the multi-agent architecture with specialized expertise and modern approaches to planning. This demonstrates that the complexity of the architecture justified by significant performance improvements. Now, looking ahead, we are scaling our AI agents across three main dimensions. The first one is compute. We've learned that using more compute in general improves the performance of the system. So we are implementing n-way search using Monte Carlo tree search to more efficiently explore solution spaces. Essentially, at each step, we would ask LLM to provide, let's say, 5 instead of 1 answers and choose the best one. And for capabilities, we're aiming to develop 100 times more specialized agents. across different domains, including infrastructure, deployments, code. That would create a much more comprehensive and capable system. And for evaluation, we're building multi-model benchmarking that continuously improve as new LLMs would be released. So we can make a call on what's better and switch very fast. And our end state goal is an extensible architecture that autonomously improves when new LLMs are released. That in return creates a system that gets better over time without us doing any work. Thank you for your attention. And if you're building your own AI agents, I'd love to hear your experience. You can connect with me on LinkedIn or on X. Those who are interested in exploring this further, I recommend checking out LangGraph agent orchestration framework or OpenEval's library for evaluation. And also check out Anthropic guide to building effective agents. And I'm happy to answer any questions you may have.